So just before we begin, can the people in the back row quickly give me a thumbs up or thumbs down if you can read this? Good. And I think we are almost ready to start. My clock shows 15 past. Good morning, everyone, and welcome to my presentation on troubleshooting SQL Server spatial query performance. My name is Michael Rees. I'm a program manager in the SQL Server engine team. I, among other things, have been the program manager responsible for introducing SQL Server spatial indexing in SQL Server 2008 and have been what's called the scenario owner for Beyond Relational Data, which includes spatial in the SQL Server 2012 release. So let's start very quickly. So as a caveat, I already mentioned that before we started. This is going to be a 400-level deep dive. If there would be a 500 level, this would be one of them. So please be aware that if you don't know what spatial data is or so, please watch the presentation that Milan and I gave yesterday. That gives you a very good introduction on that. So the main query or main question that we want to answer today is, why is my query so slow? And then, of course, how do I make it faster? That's kind of the goal of the session. And in case of most of the relational database queries, the answer is, well, your index isn't being used. Now, spatial data, of course, has a spatial index as well. So how do I figure out if a spatial index is being used or not? Well, I look in the query plan. So if I have a query that is a standard spatial query, like with an st-intersect, then if the query plan looks very simple, then simple is bad. So that means there's no index being used. This is basically just a clustered index scan, and then your operation will be a CLR operation that will be executed on every single object within your row. And that's going to be very costly because these operations are a little bit more complex than just the comparison and an addition. So there's no index here. If your query plan looks like this, ugly and big, then most likely your index is being used. And you will notice by basically being able to go and take a look at this aspect here, which then says clustered index seek spatial. And yes, the statistics always, most of the time, when you look at it for a long time, you will have this exclamation mark there that the statistics are not up to date, which means sometimes you will have to hint the index as long as this sign still occurs, unless you refresh the statistics and so on, and then this goes away, and you might get a better automatic plan selection. So, as you notice, we also introduced in 2008, for any index, we tell you now what type of index you are seeking over, because it became painful with all these different XML indexes, clustered indexes, column store indices, etc., to figure out what index we're actually talking about without drilling in deeper into the actual properties of the index. So how do I get an index? Well, the first thing is, I already mentioned, you can hint an index. And actually, in my demos, because I have a lot of different indices in my demo application, I will show, most of the time will force an index, so that you also know which index I'm kind of trying to target here. So how you force it? Just using the standard index forcing syntax. Spatial indices can be forced at the beginning or at the end of a force statement. So that means that for example, if you have a relational index and the spatial index and the query optimizer chooses the wrong order, you can, for example, move the spatial index later if or earlier, so the relational index earlier if, for example, it has higher selectivity than the spatial index. And another thing is, how you can make it faster is use SQL Server 2008 SP1 or later. The 2008 RTM version had a slight imprecision, as I call it, in the cost estimation. So you always had to use the hint the index. This got better with 2008 SP1. So next question is, I did all of that. I created an index, but it still doesn't get used. Why is that? Well, the plan is being created based on cost. So one of the things that the QO uses is cardinality estimation, statistics, etc. And sometimes it might think, oh, well, it is not really needed to use, the spatial index is not going to help me, even though it might do so. But sometimes it's because the way that you write your expression. So if you use, for example, this expression, which is basically the expression I'm going to use throughout my presentation, the bad part actually is that the query optimizer really can't estimate the cardinality of this expression, because this is just a variable, and like in any T-SQL statement, that's not going to be working. So that means that if you use expressions like these, you normally have to hint to really get the right plan during your compilation. The same goes if I do a constant expression. Now, if I do a constant expression with a relational index and I say 5 greater than my column, at that point in time, the optimizer can actually hint it because it's a constant expression, so you know at compile time what it is. The problem is that these constant string expressions for spatial objects are actually underneath the covers translated into expressions that are executed at runtime. So therefore, this is really not a constant expression. So therefore, again, you cannot expect any cost estimation from the query optimizer. So how do I get there? Well, the way to get there is basically parameterize your parameter. So you're using store procs, or in this case, an execute SPSQL. And in this case, you will get the standard relational parameter optimizations. So cardinality estimations will be done on the parameter that you pass in, but it will be cached based on the first object that you pass in. So it means that if you, for example, search with your first query about data in the US, and then all your customers run queries where they search data, for example, with a query window in Europe, then their plan might be the wrong plan, because it might choose an index that is better for US type of data than for European type of data. So that means if you have high variability, you will have to, say, recompile for every execution, etc. So this is kind of general. I mean, this, what I just told you, does not only apply to spatial indices, it applies to any type of index that is cost-based in SQL. So how do we actually do spatial indexing? Spatial indexes are quite different from relational indexes in a couple of ways. The first one is, if you look at spatial indexes in normal relational indexes in SQL, you will notice that you basically can serve the result out of the index. If you say 5 equals x, you will find all the x's inside the index, and you're there. You have the result. Spatial indices are more complex, because the shapes of the objects are much more complex. You actually don't do an exact match inside the index. The index is more there to give you an approximation of the objects that you're looking for, so that you reduce the set of objects that you then actually have to do the real comparison on. And that gives you then obviously the performance. So what you do is you actually split the predicate into two. Assuming we have these 5 objects here that are inside my table and inside my index, and I come and want to see which objects are intersecting with this red diamond here. Well, first I will do a primary filter or an index lookup. What that does is it basically approximates both the index has approximated the blue objects. My query now will be approximating the red object, and they will be looking whether they're like overlapping in the approximation. Now, if the approximation is overlapping, you will get some candidate results. In this case, I get A and B, which indeed are overlapping, and D, which is not, but according to the internal storage in the index, it seems that it might be overlapping. So then in the second step, what we do is we actually apply the original filter. So now we are taking the CLR expression and do the exact tracing and see whether they're really overlapping or not. Now, this, of course, is the expensive operation. So making sure that we have a very close approximation in the index, that's important. Also note that the index step there guarantees us that we will never have false negatives, but there will be false positives, meaning there will always be more returned than the actual result. If you ever see us return less in the first step than the result should be, then we have a bug in the implementation. Now, we have some tweaks to this, and I will go into that later on, that we can actually skip the secondary filter step because we do some additional optimizations in terms of data that we capture in the index. So you can actually have a better efficiency even than with the normal mechanism that I describe here. So when we want to take the index and store it in the database. There are a couple of ways to do so. Some database systems use what's called a spatial arc tree. We basically decided that we have one index construction or one table construction inside the database, which are our B+ trees. And what we wanted to do was, in order to be able to be done within like the amount of time that we had, to map the spatial index on top of B+ trees. Now there's an issue there in the sense that B+ trees are very good at indexing one-dimensional data. Spatial data is two-dimensional, so we have to make sure that we can map the two dimensions of the spatial data down into the one dimension of our B tree. And the way that we do that is basically add some level of indirection, like what we always do when we have a problem in computer science. So let's look at what we actually do here. So we need to have a locality preserving mapping of the 2D spatial down into the 1D space. Now there are a couple of ways of achieving that, but the main goal is that really we have to have objects that are close to each other, should be close to each other in the index. We should avoid having them like separated across multiple different places. So how we do that in SQL Server is the following way. If I have a planar index, meaning an index on the geometry type, basically we require a bounding box because your universe that you have is basically infinite on the edges. So we don't know how big your world is, so you have to give us, for the index purposes, kind of a bounding box that we know within where we actually do our indexing. And then what we do is we basically define grids. And the grids then are being used to map the objects into the index and map the two-dimensional space down into one dimension by basically numbering each grid cell. So this could look like this. I have here some map, that's the area bounding box that I'm interested in. And in this case, I basically go and say I have a 4x4 gridding, and I start numbering it. Now, the numbering that I do here to get the locality is not 1, 2, 3, 4, 5, 6, 7, 8. Instead, it's what's called a Hilbert space-fitting curve. So some mathematicians in the 19th and 20th century were all interested in mapping higher dimensional spaces to lower dimensional spaces and came up with all these mappings. And we choose one, which is the Hilbert space fitting. So basically, the numbering is now 1, 2, 15, 16, 4, 3, etc. This makes it following that up here in this space, we actually have the locality that we want. Now, there are still some places where we lose locality, but it's kind of an optimal way of placing it. So once we've done that, and we basically put each one of these objects into these cells, the next step is that we, for example, then store them in the index. So that green polygon that we have here is now located in cell 3, 7, 8, 9, 10, 12, 13, 14, 15, 16. And we do that for every object. So that means the index actually has more than one entry for each object, basically one entry for each cell. Then if I, for example, have a road like this blue line here, and let's assume the blue line is in 15, 14, 9, and 10, I basically do the same when I run the query that I do what we call the tessellation of that object into these cells. And so now what I do is I take this set of cells and do a join with my index to see, do I have a potential overlap. Now, as you can notice, some of these cells, the objects might be in the same cell, but they might not be overlapping. So that means I'm getting basically an approximate result. So the next step then is basically I do that intersection. So in this case, I have 4 cells that it might be intersecting with. And so what I do then is I do the secondary filter step that I mentioned earlier, where I go and do the actual comparison. And in this case, I'm basically getting an intersection in this example. The geography type is a slightly different, but still the same. In the geography case, I basically have no bounding box because I have a limited ball on which I have my data, so there's no need for having a bounding box. And but I have this kind of round thing that is not completely flat, so I need to kind of do some projections in preparation. So what we do is basically we take the Earth, we cut it through a hemisphere, and then we basically do a 2 top-level projection. So that means we take the 2 hemispheres, project them, and then we put them together. And once we put them together, we continue the same way that we do over here by doing the gridding, etc. Now, the story is a little bit more complex. We are actually adding multiple level grids. By having multi-level grids, we can get a better adjustability of the index onto the different sizes of the objects that you have. So it allows us, for example, to have small location objects that are just points to be potentially a little bit more precise in terms of the resolution of the lowest level grid cell compared to a big polygon that denotes, for example, a continent. So that gives us more adaptability, but it also gives us a little bit better performance going forward and a bit better management of the index. What we have in SQL Server 2008 and 2012 is we have 4 levels of gridding. The grid subdivision is customizable when you define the index. And you also have a way of customizing how many cells per object are being needed or being stored. That last one is important because if you have lots of different spatial data inside your table, you might have lots of points, and then you have, let's say, that big kind of object that spans a lot of cells. You want to avoid that this big object is basically hogging all the statistics in your index. So you want to make sure that you have a little bit of balance in terms of how the objects are distributed in the index. In SQL Server 2012 now, we also added a new index mechanism that is the new default gridding index mechanism that is an 8-level cell nesting. And in that case, you cannot change the grid density. So let's go and look at an example. We have this donut-shaped object here, and let's assume that the black border there is basically the bounding box that we have for the index. So what I do now is I basically do, in this case, I do a 2x2 grid on every level. So I basically go down at each level, and I have now this kind of shape approximation of the cells that are kind of either touching or covering or somewhat involved with that object down there. So as you can see, we are getting a pretty good approximation here. Now, the thing is that I don't want to keep the top-level cells at each level inside my index. I only want to keep one cell in my index and then code the information, what is the hierarchy. So what we do is that each cell gets a hierarchical ID, which we call the cell ID. In this case, for example, it's the fourth one in the second one within the third one within the first one. Or I think actually, sorry, it's the other way around. So it's the top level fourth one, then it's the second level within that one, then it's the third one within that one, and then it's the first one within on the fourth level. So that's kind of how we encode it. Now this gives us, of course, information that we can use with prefix matching to make sure if I compare two objects that have different levels of nesting, I can actually very easily determine whether they overlap or not. Another thing that we do is if all the cells within a bigger cell are covering the object, we basically only store the next higher level. So that means we, instead of having 4 entries, we will have 1 entry in the index. And finally, as I mentioned, the user can restrict the cells of objects using that parameter. The default is 16. I think the maximum is 8,192. Now, there's a really important aspect, which is what happens if my object is either partially or fully outside the bounding box. Well, there is a kind of a cell 0 out there, which these objects are being placed into, or these parts of the objects are being placed into. Now, the cell 0 is very important. It's both good to be in there and it's bad to be in there. It's good to have objects in that outside the bounding box if your query window will always only look at objects within the bounding box. Because then you can basically say, I never have to look at anything outside in cell 0, which is good. However, if I have just a tiny bit of my query window go outside of the bounding box, then every single object in that cell 0 will have to be taken a look at because there's no further subdivisioning of that cell. So that means if your bounding box, let's say you have a bounding box across, for example, the Netherlands, and you are starting to look for something in Switzerland, then that's not good. Because now you not only look at the things in Switzerland, but in China as well. And so that's kind of, you have to be careful with that. So how is the index internally implemented? It's implemented as an internal table, similar to XML indices and full text indices. And what we do is we then basically rewrite the query to use the table. And that's one of the reasons why that index plan looks so complicated. So the internal table contains basically 3 rows. There's also the SRID column there that is not really being used at the moment. So you can ignore that for a while. So if I say create spatial index on this geography type, basically the index will look like this. It will have the primary key to go back to my base table. It will have the cell ID, which is now encoded in some binary format using the hierarchy ID type that we have in SQL, basically, although it's a custom implementation because it's a bit smaller. And then we have the cell attribute. So the primary key goes back. It has 895 byte limitation because it's basically has to account for the 5 bytes of the grid cell ID that will be used to cluster the index together with the primary key. Then the SRID basically is there in case we want to make optimizations based on that only objects with the same SRID can be operated on, although I think that we are currently not doing that. And then the cell attribute is very important. For each object-cell relationship, we basically record the state on how they relate to each other. Basically, if we see that the object is bigger than the cell and is covering it completely, we give it a 2. If the cell is definitely within the cell, but it's not completely covering it, in that case, we give it a 1. And then the 0 is kind of when it's neither 1 or 2. And that's primarily when it's kind of touching, because the numbers that we're using for the geospatial coordinates are floating point numbers. There is kind of a small area that we give for error to account for the imprecision of the type. So now the interesting part is that if I have an object that covers the cell, there is a guarantee that it will always intersect with anything that lives within that cell. So if I have my grids designed in a way that my objects, at least my query object is covering it, then I can basically determine that these 2 objects intersect without having to do the expensive operation afterwards. So this is an additional optimization that we have that allows us to even avoid the last secondary filter step. So let me also quickly talk about the new spatial index that we have, that is the default index. It's basically an auto grid, so we are using 8 gridding instead of the 4 that I explained to you. And there are no gridding parameters needed because we basically have the density fixed. And there is also different default numbers of cell per objects for this than we have for the other case. So it's 8 and 12 here. For the other one is 16, but you still can override it. Now, the reason why we added this new index is that we give you more stable performance for windows of different sizes. One of the things that we did was we designed the default index to be the one that is kind of not necessarily the best one, but a predictable one and something that you can start out with. And we did that in 2008, but we noticed that depending on what the query window was, that the performance differences was quite tremendous. So we basically get a better predictability with this index. We also, for certain values, we're going to be faster. For some, we might be, like small queries, we might be a little bit slower because we are doing more processing because we have 8 levels that we have to take a look at. So here's an example. The interesting part here is primarily, you see how the blue line is jumping all over the place? That's the line that is the default behavior for a set of queries against congressional districts as query windows. That just shows you how unpredictable the old default index was. In some cases we were good, in some cases we were bad, depending on how the query window looked like. The red line, it's still jumping around, but it's much more predictable. It's much in a smaller range. So that gives us a kind of a little bit of a better default behavior. Okay, let's go to the next slide here. In terms of index creation and maintenance, you basically have a new create spatial index syntax. And what you do there is you basically have a set of parameters. If you do an index on geometry type, you have to have a bounding box specified. I already mentioned that. And then optionally, you can specify the grid density level. by saying basically which low, low, medium, high means that, for example, the level 1 is low, level 2 is low, level 3 is medium, and level 4 is high. And then the cell per objects number. If you have a geography type, you have the same two options, but you are not going to give the bounding box. And in both cases, you have this using as kind of an indication which ones of the tessellations you want to use. At the moment, basically, we infer it out of the type. And now that we have the new autograde index, you basically have now geography grade and geography autograde as options there. And that's basically expressed down here. If you then want to do alter, drop index, etc., use some standard alter, drop index commands that you know for other indices. So I think I have shown you enough of slideware. Now let's go and look at some query plans. So I have here some interesting data. I have basically two data sets that I will be using. The first one is a data set that has H1N1 data from 2009. And then the second one is actually some Dutch data that I got from NAVTech. So let's look at quickly here H1N1 data. So that's about, just for the US, it's about 5,000 entries. And if you look at the spatial result, you will notice these are dot or point data that is basically identifying an incident of H1N1 in 2009. In addition, I have a table of counties in the US, which you will see is basically just each county in the US being represented as a polygon. So now my query that I would like to do is, and as you notice also, or what I probably should point out, both of these data here are geometry data, which means I will have to have bounding boxes for my queries. So let's take a look at what the query that I want to analyze looks like. I have here a query that basically goes and says, for any county within the state of Washington, visualize that. And this is the query that is really going to do an index usage because it's doing an intersection there. It basically goes and tells me, find me all my H1N1 occurrences in any one of the Washington state counties. And then put a buffer around it so I get some better visualization. So if I run this query, and I shouldn't have an index at the moment, you will notice it's taking a while. Because now it's basically looking at each one of the rows and does the join here. And actually, yeah. So as you can see, it's running and running. So let's just stop it. I know it should be faster. So what I do is now I go and define an index. But since I need to have a bounding box, I now need to figure out what bounding box do I choose. Now in this case, I chose to use a bounding box of the US because I decided that I might want to also look at other states and not just Washington state. But of course, if I want to look at Dutch data, I would have to use a Dutch bounding box. But unfortunately, I don't have the polygons of the Dutch provinces or whatever they're called here available. So one way of calculating the bounding box is now that I go and basically take the most extreme points of any one of the points that I have within my map for US countries. Now there are two ways of doing that. One way is that I go and do an envelope aggregation and then get the points of the envelope. Or in this case, the envelope aggregation although only works in 2012. In this case, I basically just do the envelope and then do an aggregation over the external points of every one of the envelopes, which is basically what works in 2008 as well. So if I do that, I'm calculating the coordinates. So I'm going to use those coordinates now inside my index. So I'm using the bounding box here. The other thing I do here is I'm using a high, high, high or 4H gridding. And that's done because the data that I have are point data. And so for point data, to have the best optimal approximation, you want to have a really high grid density level, which means each grid will only have a few points in them. That will hopefully give you better performance later. So the index has been created pretty fast here. Now let's run the query again. Same query here. And note, in this case, I don't have to hint it because I'm just doing table joins. And of course, the query is already done. If I look at how long it took, it's 1 second. That's a pretty old laptop I have here. And obviously, the result looks like what you would expect. And let's look at the execution plan quickly. And so you see it's a complex execution plan. And if I head over here, you will notice that there is a spatial index seek here. Let me move that a little bit over so I can zoom in. So you see that there is a spatial index being used. So let's go back and run some more queries to kind of show you what we can do with these indices. I have the same data here as H1N1 data, but this time as a geography type. And I also have this time some European data. And particularly, I have here, I will run this query quickly here, some world data. And I basically get the countries that are using either the euro or the Swiss franc, because I'm Swiss, or the Serbian dinar. That's because Milan is, who is working with me on Spatial, is from Serbia. And so I run this, and this case basically all these countries. And if I visualize it, you will hopefully notice that this looks kind of like the member states that are using the euro, the Swiss franc, or the dinar. At least I think that's still the countries that do that. I have to figure that one out later today. So I basically defined a view on that. And now I'm going to run the query again between these two and see what are the H1N1 cases in those countries. And as you notice, the query is taking a while because I don't have an index specified. So it's probably going to take about 17 seconds or so, or even more. And this time I would like to kind of just letting it run so you can feel the excruciating pain that we have by running those. And the important aspect here is now that I have a geography type. So in the geography type, when I define an index, I will not have to use a bounding box. And that means one of the changes we did between SQL Server 2008 and 2012 is that we improved the precision of some of our operations inside, which means that we actually can improve some of the resolution of our operations a little bit as well. So now it's done. It actually took a minute. Just to show you, the execution plan looks very simple. And if you zoom in, you will notice that there is really, no spatial index being used. So now let's go and define the spatial index. As you notice, I still have high on my H1N1 data because it's still point data, but no bounding box this time. The index got executed very quickly again. And so now I execute the query again. And indeed, we go from almost a minute down to about 2 seconds in response time. So these indices, while they might be complex, as you have seen earlier, really have a huge impact on the performance in terms of improving your spatial query. So now let's show some other queries here. This is some data that I have about the Netherlands. And the query that I want to look at in particular is the following. I have here geolocation that is the RAI center, or somewhere outside the RAI center, that we took with our GPS device on the phone. And now I want to see all the roads that are within a kilometer distance of me. So I'm running this query, and this time I use an ST distance, which is actually now supported in 2012 as a query plan as well. And I run this, and again, it's taking a long time. Well, why is that taking a long time? Look at the from clause up there. You will see that I say highways with index 0. That basically unhints any index use. So I'm running the query without using any index. Just to show you, I'm canceling that for now. Or actually, let me just show you quickly what the use Netherlands. And let me show you the select count star from highways, finding the home button here. And you will notice that this table actually has 1.5 million rows. So that's why it's taking that long if you don't have an index. So it's still executing. I just stopped that. I mean, everything that goes more than a minute should not be running. So what I do now is I basically want to show you how an index helps, but also how the different indexes help differently. So the first step I want to show you is how this query performs if I have the default indexes from SQL Server 2008 running. So that means I have them installed with geography MMMM, that's the default tessellation, with 16. And I do that both on my highways and my point of interest, which I use later. So I run the same query now again. Now in this case, I actually don't hint an index because at the moment, the optimizer will choose this MMM index as the default index. At least it did when I was setting up the demo. So let's see how it works. Oh, it's already done. Well, previously it was like running until I don't know when. So now we are done in about a second. So let's look at the actual response time here. Oops, I didn't put on statistics here. Let's do that quickly. And also let's take a look at the query plan. Rerun the query again. Since it's so quick, doesn't matter. Actually got even quicker because probably the data got cached. So if I look at it, it's 0.4 seconds. So we went from over a minute down to less than a second. And just to show you the query plan here, you will notice, oh, actually, you know what? This actually cheated on me. This actually now removed it got the statistics updated and decided that it wanted to use the right index. So let's just hint the bad index here with index, and that's the this name here, and run it again. And so now we see it's 2 seconds, still better than before, but not as good as we can get it. And the execution plan now here is, just to zoom in here, or not, let's see. It's the geography MMMM index that it's using. So with the default in 2008, we would have gone from over a minute down to about 2 seconds, and I don't know why this one is opening. And so now, of course, you already have seen also what the new default index does. Now in this case, the default index with its new tessellation scheme with 8 levels, etc., is giving us an even better performance than before. So it means that now I go from over a minute to 2 seconds down to basically half a second. And so you basically have seen that. Just running it again to show you what the execution time here is. It's basically, in this case, 0.2 seconds. So now another thing that I want to point out is that SQL Server's spatial indexing is actually very clever in terms of the query optimization because it recognizes certain equivalent expressions and will use those equivalences to still find you a plan even though the operation might not be the same. So that SD distance that you had there actually gets internally translated for the index lookup, the primary phase, into an intersect over the object with a buffer. Now, so they are equivalent. However, if you write the SD distance as this, you might still be faster. And the reason why you might still be faster is that the secondary phase that you run out later will be using the method that you have specified inside your predicate. So in the first case, you will always run an SD distance on the secondary step, while in the second case, you will be running an SD intersect in the second step. And according to my developers, the SD intersect is actually faster. So let's take a look at here and run the same query with the same auto index, but run it with that reworded expression and see what we get. Again, the query is executing very fast. And you will see that the execution time in this case is about the same. But that's primarily because we have a very high efficiency of our filters. So let's take a look at the filter efficiency. I mentioned that we have this first phase and the second phase, and that we want to make sure that we get as little false positives in the first phase. So we can take a look at how that actually happens. We have a built-in function here, a method on our spatial type that is called filter. What this does is, if there is an index present, we will only basically apply the first phase. We are not doing the second phase. So this helps us in doing some analysis. It also helps us building applications where we want to do post-filtering ourselves, etc. So in this case, what I do is I basically look at the number of rows that are being created by, or a number of objects that I'm getting by the filter step at the beginning. So in this case, it's 1075 if I use the auto index. Now, just to see what we are actually getting as real results, we are at 928. So that means we only have about 150 additional objects that are false positives, which is actually pretty good. That's like around 10% false positives. Now, if I, for example, compare this with the previous index, that was previous default, I run this, you will notice that the previous index gave me 19,000 candidates. So in this case, the thing was the other way around. Now I suddenly have 95% of the data I have to throw away in the secondary step. So that's why choosing the right index here is very important in order to be able to get the right filter efficiency. Just to show you, another interesting aspect is that SQL Server, unlike some of our competing products, actually knows how to do commutative operations. So in this case, I have rewritten my query to do the intersection on my probing object, and the index, of course, is only on my geography type. And even though I don't have an index on my variable, of course, you will notice that doesn't matter. We are still going to get an index. Let me show you the index here. So we still have a spatial index over here. So this is something, for example, that our competitor with the big O in his name is not doing. You have to write the query in a specific order to get the index being chosen. However, unfortunately, it's not all easy peasy here. Unfortunately, it depends on where the equal 1 is placed. So you might have noticed I always say st intersect equals 1. So the comparison always comes at the end. St distance greater than something or less than something. So the placement of that comparison unfortunately matters. So in this case, I try to write a query where I say 1 equals st buffer intersect and hint the index. So if I hint the index, of course, I get an error message because it can't find a plan with the index. Because if I write it this way, unfortunately, my query optimizer will always decide that it will use a plan without an index. So it's not all easy, but just always remember, put your comparison at the end. So let's go back and continue a little bit. The spatial queries that we support with the index are basically all these that you see here on the screen. So st intersects, equals, contains, distance, etc. The ones that I have bolded are the ones that are newly supported with the index in SQL Server 2012. Now, in the geography type, the new ones are particularly new also because these are new operations. We didn't support them in 2008, so we are supporting them now and also with an index. In addition, we now also support so-called nearest neighbor queries. Now, nearest neighbor is not an operation per se on the spatial type. It's a query pattern that people use that say, find me the 5 closest Italian restaurants ordered by distance. And so basically that's what that query pattern we now recognize and are going to use an index on it. I will show you that later. Now, let's go quickly more in depth in understanding how costing is done so that we can kind of understand how should we further optimize our indices. The index, basically, the statistics are based on that cell ID in form of a try. And what that means is basically, if I have a sniffable window object that gets compiled, then I basically do a prefix lookup based on that try. And so I'm going to use the statistic on that try to determine which index to use. However, it's always done on a sniffable window if I do that through parameters, for example. And as we talked earlier, there's no costing on any of these. One thing that you can do is, if you have different types of query windows, you can have more than one index specified on your spatial column. So what you can do is, if your benefit is great enough to justify the additional cost, is to go and do a quick check. Is my query window here or there? And then depending on which one it is, you then can decide to hint another index in your query, for example, to make sure that you, for example, if you query over European data, you hint the European bounding box index. If you query over another area, you will use that area. Or if you have a query window that goes more against point data, etc. So there's different ways of how you can use that to further optimize it in writing your own code in store procedures to choose the index that you want. So now that we have all that information about costing, about other things, let's look and try to understand why that query plan looks so complex. So if you look at that, you kind of wonder what's going on here. Well, the first thing that you want to do is, if you are looking inside the index, we of course want to make sure that the index lookup itself is efficient. So what we want to do is we want to minimize our I/O and random I/O. So that means small windows should only touch small portions within the index. So let's look at an example here. We have a cell 7.4, and then we have our spatial index. Now let's see, if I have this as the query window, what does it match within my index? Well, it matches any data that is with cell 724. Now all these items are clustered together because that's part of our index cluster key. So they will all be next to each other, so we will basically can do minimal I/O on that. Then of course we have to touch all the ancestors. Now they are probably somewhere else, not necessarily clustered at all, so that's an additional 2 I/Os at least. And then I have all the descendants. Now the descendants are clustered with my parent because of the way that the cell ID gives us locality. So that basically means I have kind of 3 I/Os here, or ranges of I/Os that I have to do in order to be able to get at the data inside the plan. So now let's look at what's happening here. The table-valued function that you see here is basically taking the query window that you provide as a parameter or as the probe from another table, and it applies the tessellation function at it. Then it gives me the ranges that you have seen earlier of the index to kind of do a join to identify which are the cells of that object that it basically fits into. Then I might remove some duplicate ranges that I have and potentially sort it. And then I basically do a nested loop join against the spatial index to figure out which ones are actually candidates in there. And so this is basically the primary filter step of the index. Now, if we look at that tessellation, the tessellation actually is very important in terms of giving us performance and precision, as I mentioned earlier. So here's just a view of some format and seeing how it tessellates with 64 cells versus 256 cells. And you will notice that the blue parts, which are the parts that are actually fully contained cells, increase in terms of the more precise you're getting. And this is good because that means that I will be able to use my optimization that I mentioned earlier around not having to apply the secondary filter step. And the partially contained cells, if they get less, then that means, again, I have to do less of the post-processing. However, there's a trade-off here. And the trade-off is that I have, on the one hand, the primary filter time will go down the more precise I am, so to speak, but the combined primary and secondary filter time goes up, it goes down the less precise I am. So if you look at the maximal cell for a query window there, it actually is decreasing along the x-axis. And the primary and secondary filter time is basically kind of a trough. So there is an optimal point there of combining the maximum cell for that query window that you have to probe into the index, and the time it takes to actually look up in the index. And then the more precise that is, the smaller is the post-processing. However, but the higher it's the join cost on the index, and the lower your maximum cell for the query window is, the more false positives you will have. because the less precise it is. So let's look at an example here. So what we did in SQL Server, before I show the example, in 2012 is we introduced a new hint. So now you can give a spatial max cell hint on your query to basically move the dial between these two locations. And the reason why we did that was because it actually helps people to kind of optimize in on that trough inside that red curve there. And so this is how the syntax looks wise. It is being chosen if an index is, so if you specify it, it's being used if an index is chosen by the plan. It will not force an index. There is a default that you can override, and the rule of thumb here is the higher values make primary filter phase longer, but reduces work in the secondary filter phase. So if you have dense spatial data, you want to increase it. If you have sparse spatial data, you decrease it. And in general, we already have seen how you do index hinting in the other case. So let's go and take a look at how this looks like. Going back here. So remember this query that I had with respect to joining Washington State with my H1N1 data. So I'm running it again. In this case, it is using an index. Let's see how fast it took. It took about a second here. Now I go and specify a spatial window max cell here. In this case, what I do is I actually lower the cell number because my data is pretty sparse, as you have seen on the result. And in this case, if I run it, you will notice that my result time is now 3 times as fast. So it's 0.3 seconds. So it's an important thing to do that. And again, just to show you, the filter efficiency here, I'm running it first in terms of how many results I'm getting. I get 85 results. If I use the filter, the primary filter, I get 88 without that query hint. So that means I actually let's see what happens if I do the primary phase with that query hint window. And I actually see that I'm using more. So in this case, the query that is running faster will actually have more data being analyzed in the secondary phase than in the other case. And that is probably meaning that for that data set, for that query, the primary filter phase was longer and more costly with having a higher tessellation on my probing query window. So this is an important kind of way of like balancing these things out. Oops, let me go back here. So other things that we do is we actually give you the ability to use relational predicates to optimize further. So if you have relational data, you can use that, and it will be pre-filtering your spatial index lookup as well. I already mentioned the new matching types that we do. So we do nearest neighbor query, we do distance query. We've seen that happen, how we translate that into intersects. I've shown you commutativity. We also recognize duality, meaning A contains B is the same as B is within A. And so if you write either one of these queries and one of those columns have an index, we will choose the index regardless of how you write the query. You can have multiple spatial indices. I already mentioned that. And the autoreferences is always a window object. So what we will not do is, even if you have 2 indices, we will never make use of both indices because we notice that this is actually in most cases slower than just using one as a probe into the other. A couple of other things that we did in SQL Server 2012 in terms of performance improvements is that the spatial index build time for point data has been improved because we generally improved our point data management inside the CLR implementation. We further optimized spatial query plans for ST intersect and distance over 2008. And we also optimized ST buffer, specifically also giving a lower memory footprint. So now let's look at the spatial nearest neighbor query. The main scenario here is really give me the closest thing to where something else is, and give me the top n of those. In SQL Server 2008, if you write such a query, you will always get a table scan. So you will not make use of the index. In SQL Server 2012, we will use the spatial index. However, we will only use it if you're following the query pattern that I show you here. So you always say select top X, or you can also use fetch first, the new top X replacement following the SQL standard. Doesn't matter which one you choose. And, of course, you have the order by distance, so that you get it in terms of nearest. But also you have to say distance is not null. And that part is important because SQL Server, unfortunately, orders nulls first. And so you want to, kind of for semantic purposes, you never want to have the null values first. And the null values could happen here because you have different SRIDs that will lead to null, or you might have just null values in the column, which then lead to null on the operation. So you have to have this inside your where clause. So if your query looks like order by, distance not null, and give me the first n, then we actually can identify this as a nearest neighbor query, and we will go and do the right thing in terms of running the query. So let me show you this here. Going back to my Netherlands data. And in this case, what I do is I want to basically look at all the top 20 nearest points of interest that are not tourism category, because I want to play local here, around the Rye. So if I run this query, you will notice this is not using an index. Because I hinted it out. Let me quickly fix that, because I assume that this updated the statistics as well. And so this is taking its time as well. And I'm just canceling it because, again, these queries are just taking too long. So now let's look at what the query would do if I have the old default index. Now the result is already here. And why is the result already here? Well, let's look at the oops, I forgot to include the query plan again. So let's rerun it. So let's look at the index plan here, and you will notice again it looks complicated. So there is obviously a spatial index somewhere in here, and here it is. And let me just do now without the hinting and see which index it's choosing this time. Just to show you that it actually chooses an index even if I don't force the index. And as you can see now, in this case, I still get the MMN index. But if I use the new default index down here, I'm going to be even faster than what I was before again. So you notice now that I'm sub-second. And now I'm basically 0.3 seconds. Now, point of interest, unlike the line strings, is actually point data. So let's see what happens if I follow my general recommendation to use a 4-level grid high density index and use that instead. If I use that one instead, I actually notice I'm going to be even better than my default. Well, in this case, I'm about the same. But it actually can lead to even better performance sometimes on certain data if you go point data with high. In this case, you can see that the autograde index was basically pretty close. The difference between these two numbers is statistically not significant on this laptop. Okay, so you have seen now that we can do nearest neighbor queries, that we now will use the index for those. Let me just show you a comparison. There was actually a workaround in SQL Server 2008 where you basically say, get me all the closest, give me all the objects within a certain radius, and then give me the top closest 5 out of that radius, for example. And then you just had to select the radius big enough to get all the data you want and small enough that you don't get too much data. And so we have been comparing now that approach, which is the red line, with a 10-kilometer distance against basically our auto-detection of the nearest neighbor query pattern and using our index that way. And as you can see, in cases where we have high-density data, where there are lots of objects within 10 kilometers, the new approach is performing much better. So, for example, if you look at USC Biotech, there are lots of points of interest there, so it takes a long time. On the other hand, places where there is almost nothing happening, so if you go, for example, over there, USA rural Idaho, which is the second to last point, there's basically almost no data there. So basically both are kind of behaving the same way. So, but it means that we are basically giving you pretty good performance that way. There are some limitations on the spatial plan selection. I already mentioned, whenever a window object is not a parameter, you have to basically often hint the index. The other thing is sometimes you get interesting messages. And there's a message here that you might get that says the query processor could not produce a query plan for a query with a spatial index hint. And then there are a couple of reasons that it lists. You have seen that earlier when I was trying to do 1 equals. And basically, we kind of give you a lot of reasons and just read them and act on them, basically. If you get a message, for example, could not find required comparison predicate or so, you might want to look at the index and really see, is that a supported query with an index? And go and fix it. In terms of index, the index can be built in parallel, which is good in terms of index creation. You can partition it with either by aligning it to the partition of the base table, or you can place it unpartitioned in a separate file group. You can only do full rebuilds, however, and so that's a little bit of a kind of a caveat. And we added new catalog views and TDL events, and I will show you that in a minute. There's also DBCC checks. Will be checking the spatial index alignment if you use it with logical checks. So that's similar to the XML index. And we added a couple of supportability store procs that help you actually look at what is in the index and how to use that. And that's what I will be showing in the end. Also, in SQL Server 2012, we have added index row and page compression. So that gives you the ability to make your index smaller and faster because you will have to read often less pages. So the indexes are up around 50% smaller, and the queries actually, the 0 to 15%, that's the worst case. Often, if you have lots of pages to read out of an index because you have really big tables, it will actually be faster because the I/O is going to be the costly part, and you save on that. 2 things that are not supported is we don't support online index rebuild yet, and that has to do with that the SQL spatial types are implemented as large objects, and the large objects underneath are not allowing you to do online rebuild yet. And we are not supporting it in the database tuning advisor because the kind of mathematics behind selecting the spatial index is quite a bit more complex and different from the way that you do that for standard indices. This is just kind of a caveat. I hope everybody is using these settings today anyway. We basically kind of require you these settings to be there for the index to be chosen. And as I mentioned, the partitioning is working. So you can default partition it to the same file group as the base table. So if you have a partitioned base table, your index will be partition aligned. You can override it by saying on file group name or on default. And if you specify that, then everything gets placed in, of the index will get placed into that location. You cannot change the base table's partition scheme unless you have put the index into another place. So there's no ability to go and auto-repartition the table and the index together. What you will have to do is you will have to drop the index, repartition the table, recreate the index to recreate the partition-aligned index. Here are the catalog views. I will go into those in a minute, so I jump over those. We also have new spatial histogram helpers. These are built-in store procs that actually give you the ability to peek into the index, and it gives you a nice visualization over here of how many objects it will find within each cell. So that can kind of help you, give you kind of an understanding of how many objects you might have to intersect with. And you can build nice heat maps over that. If you go and, for example, have a custom app that you use, take that output and do some heat map over on Bing. That's not part of the product, I just want to say. And here are the spatial geometry support procedures. Now, these procedures, if you run them, will give you a plethora of information about what's happening when the index gets processed. Unfortunately, we can't run them automatically because each one of them takes a couple of minutes to run. It gives you information about the index with respect to a certain query window. There are about 10 to 15 core properties, and then there are like 50 more that give you additional information. So let's look at how you, for example, invoke that. There are two flavors to each one of those. So first one is that you have a set of two for the geometry and for the geography type. And then you have one that gives you XML back and one that gives you a side effecting table back. And so depending on whether you want to operate on the result or not, you can use one or the other. But the data is the same. So what you give is the table name, index name, whether you want to have the extended report or the condensed report, and the query sample object that you use to probe the index. And then the result is either key-value pair or as an XML output. And here are some of the return properties. So you will see how much rows are in the base table, how much rows are in the index, how much pages are we using in the index. Another thing that you get back is, for example, how many numbers of rows are being selected by the primary filter, how many rows are selected by the internal filter, which is basically when the secondary filter is not being called. It gives you percentages, and so the interesting percentages here are the internal filter efficiency. That basically indicates whether we do that additional covering cell optimization. It also gives us the primary filter efficiency, which is basically telling us how close are we. So that's kind of what we did earlier with the filter predicate and the intersect predicate and counting how many rows we are getting. That's basically the same thing as calculating that number down there. So let me give you a quick demo on these operations. So again, here I'm running using my Netherlands data. And let me just show you kind of the spatial indices that we are having. So this is kind of what you see. You get the name of the spatial indices, and then you get all these index properties here. And then it gives over here, what is the spatial index type? Geography in most of these cases. And what type of tessellation scheme we have used. So you see geography grid and geography autogrid are the two that we currently support, and we have used both of them. Now, in addition, I can go and look at the details of what I actually used for my tessellation. And so what I do here is I look at all the indexes that are defined on tables that have an auto index specified besides other indices. And I look at what are the tessellation information that we have used. So in this case, I basically have two geography autogrids on two tables, but each one of those tables has the standard grids as well. So I can now look at what are the options here. None of them have a bounding box because all of them are specified on geography type. And then you see over here, the first three were the manually graded indices. So you see two of them are medium-medium, one of them is high-high, and then the two lower ones were auto-grids, so they didn't have any entry here. Cell per objects were the defaults in all cases, so that was 16 and 12. So you can basically just look at the metadata here to find out what's going on. You can also look at sys internal tables, and you will notice that you have the extended index tables there that are actually containing the data that is being used for storing the index data. So now let's look at the query again. Remember the one about the roads around the Rye? Let me just run it again and kind of show you the result here quickly. So this is kind of the result of all the roads here around the Rye, which is this location here. So now let's see and say, well, which index should I use between these MMM and the auto index? We have seen earlier the auto index is better than the MMM index. So what I do here is basically I use that spatial geography index store proc, and I pass it the table, the index name. I only want to have the condensed version of the output, and the query window, which in this case is the point here at the right. And I run this store proc to kind of figure out what's going on. So the query shows me this result here. And the interesting aspect here is I can, for example, see two interesting things. First, primary filter efficiency is 4.7. So that means only 5% of the, in the first phase returned selection is actually real result. The other 95.26% or whatever is going to get thrown out in the secondary failures. The other thing that we notice is that the internal filter efficiency is 0. Well, why is it 0? Because we are primarily doing point and line string data. And of course, point and line string data is not covering any cell. So in this case, internal filter efficiency is 0. That means we actually are applying 95% of our time in the secondary filter on things that we throw away. So that's not a good index to use. Now let's look at the autogrid index. And as you probably remember using the filter indication there, this is taking a little bit longer. When you remember, we got there in a filter efficiency of, I think, about 90%. And I'm kind of wondering why it's taking that long. There it is. So if you go down here, you will notice, oh, sorry, it's 47%. So we are much better in our primary filter efficiency. Still, our internal filter efficiency is 0 because it's point and line strings. And for example, we see that the percentage of rows not selected by the primary filter is 99.8%. So we are basically only operating on a very small data set here. So that shows you how you can analyze the index and then, for example, choose between one or the other index. So to conclude, let's give me some high-level spatial tips on index settings. And these are best practices variations, recommendations, and your mileage may vary depending on data and phase of the moon and other things. So my recommendation is if you use SQL Server 2012, start out with the new default tessellation. If you have point data, you might want to go with high on all 4 levels. And it doesn't matter how many cells per object you have, because there's always only going to be 1 cell per object, because a point is a point. If you have simple, relatively consistent polygons, and the default tessellation was not the best one, you can go to either low or medium, low, low as an alternative. If you have very complex line strings or polygon instances, we recommend that you up the cell per object to a higher level, because that gives you much better precision and can increase your internal filter efficiency, because you basically have more cell coverage in that context. And sometimes setting all 4 levels to high might be beneficial, although that's, again, only if you're not happy with the default tessellation. If you have lots of varying sizes and objects, then probably you have to do the store procs that I shown you earlier. And the rule of thumb for geography type is if MMM is not working, then try HHMM. That's basically at Kadiba's personal rule of thumb. So to recap, what is if my spatial query is slow? The question that I want to answer. Make sure you're running SQL Server 2008 SP1, R2, or 2012. Check the query plan for use of the index. We have seen how that works. Make sure it's a supported operation. Hint the index if you're not going to get it. Sometimes it might also help if you hint the join type to make, for example, the nested loop join into a merge join. Do not use a spatial index when there is a highly selective non-spatial predicate. So if you have, for example, a relational predicate that already gives you back 5 rows, then applying the spatial index on that is probably not going to be a good idea. And use the support procedures that I've seen. Look at the primary filter efficiency, the internal filter efficiency, and then do adjustments based on what we have talked about today. So to summary again, the new things in SQL Server 2012 is AutoGrid, spatial index hint for the query window. We support more operations. We do spatial index compressions. And we do better point-in-time data and nearest neighbor queries. Here are some related content, some spatial presentations, and for those that want to see the first part of the presentation where we just talk about the spatial data types. That was yesterday, DBI 324. Ed Kadiba has a blog with lots of information. You can also find me on Twitter or in email later if you have any further questions, follow-ups, and so on. The code that I've shown, I will be placing up onto the standard share here, so you should be able to download it the latest tomorrow if they are putting it up. And I will be tweeting about when it's available as well, so people can go and download the code as well. I appreciate your patience and your interest. We are at the end of the presentation. Thank you very much. I would like you to have, if you have questions, feel free to ask them. I'm staying around here to answer them. If there are anyone right now that would like to ask a question, please do so. Thank you. And just as a thing here, we really appreciate, as speakers, if you fill out the evals. I would love to, of course, would love you to give me all 5s. If you give anything 3 and below, I would like if you could give the reasons why, so we can improve our presentation for the next time. Thank you very much.